Oh, hi there. Well, this is Mr. Kraplin, and this is part number 4 for activity 1.2.3, electrical circuits. And now we're going to talk about parallel circuits. So the main lesson objective at the end of this lesson, students should be able to identify a parallel circuit and then also calculate voltage, current, and amperage using Ohm's law in a parallel circuit. All right, well, let's try to figure this bugger out and see what we can come up with here. So parallel circuits. So a parallel circuit is really a circuit that contains more than one path for the current to flow. And so if a component is removed, there goes our light bulb, then it's possible for the current to take another path to reach other components. So we still have this branch here that is still uninterrupted by the current flow, and it's still nice and yellow and bright. And so that's what we want sometimes. It's actually what we want most of the time. So parallel circuits. So what are the characteristics of this sneaky little parallel circuit? So the voltage across every parallel branch component is equal. So the total resistance is equal to the reciprocal of the sum of the reciprocal. We're using the word reciprocal a lot here. So what does that look like? So 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And that's all going to be over 1 to find our resistance total, okay? So that's kind of how we do this. 1 over R1, 1 over R2, 1 over R3. All those over 1 is going to give us our resistance total, okay? And so the sum of all the currents in each branch, so the current at R1, R2, and R3 is equal to the total current. And so this is called Kirchhoff's current law. And so we'll kind of look at that here a little bit more. So let's look at the example a little bit more. For the parallel circuit shown, use the laws of circuit theory to calculate the following. So we're going to find the resistance total, and we're going to find the voltage across each component. We're going to find the current flowing through each component, and then we're going to use the results to verify Kirchhoff's current law. All right, so let's go and start with resistance. So the total resistance is equal to this equation right here, this setup right here. And so we're going to take 1 over 470, 1 over 2.2K, and 1 over 3.3K. And so all of those will be over 1. And so what we get is a resistance total of 346.59. We're going to round that up to 350 ohms for our resistance total. So now let's figure out the voltage across each component. So in a parallel circuit, our voltage is going to be the same. Voltage total is equal to voltage 1, which is equal to voltage 2, which is equal to voltage 3. So that's easy to figure out because it's given to us right here. So what is the current through each component? So we're going to take our finger and we're going to cover up I, and we know that we need to divide our voltage by our resistance, okay? And so we have 15 volts divided by 470 ohms gives us 32 milliamps here at I1, okay, or current 1. And then current 2, same thing, voltage is the same, divided by 2.2K, and we get 6.8 milliamps. Okay, remember, you might get 6.818 amps, but we're going to convert that to milliamps. I don't know why this is like this. It's, all right, I'm sorry, 6.818 rounds to, or we just use 6.8, so it rounds down to 6.8. And then I3, again, same values, 3.3K, then we get 4.5 milliamps, okay? And so if we were to add all of those up, these three up, we should get something pretty close to 43 milliamps, okay? So when we take our voltage total and divide it by our resistance total, we should get this. And so again, we would add all that up and we would get something that's pretty darn close to 43 milliamps. You can also have what's called a combination circuit. So a circuit that could also contain both series and parallel arrangements. And so what would happen if you removed light 1? And what would happen if you removed light 2 or light 3? So if we took light bulb 1 out, if that burned out, that would cause a break in the circuit. And so it would no longer supply current to the other 2 light bulbs, so they would not light up. But let's say 2 or 3 burned out. Well, current would still be passing through light bulb 1, but then not through 2 or not through 3, depending on which one was burned out. So it would still keep at least 2 of these lights burning in our circuit here. And then let's talk about electrical power. So electrical power is directly related to the amount of current and voltage within a system. And so we actually have an equation for this. So power is equal to our current times our voltage. And so power is measured in watts. And so what's interesting about this is you can take any kind of device that you have at home or that you personally use. And if you know the voltage, which in most cases is probably going to be 110 volts, so that's the voltage that would be coming out of your wall. And then if you knew the watts for the device, you could actually figure out the amount of current that would be needed to actually make that device work. So just kind of another way to kind of measure that particular component or that particular setup. And we'll actually talk more about this in more upcoming videos. Hey, good job. You made it through all 4 videos. Hopefully you got a chance to finish the guided notes. And then if you have any questions about this or any of the other videos, as always, please ask.